Hello everyone. In today's lecture, we will start a new chapter named Application of Derivatives. We have seen what are derivatives. We have seen different types of derivatives, different methods of derivative. Now in this chapter we will see different applications of derivatives. The images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. So let's start with the contents of this chapter. In today's lecture, we will see derivatives as the rate of change, increasing and decreasing function, monotonic function. After that, we will move to the results on different monotonic functions. We will see tangent and normal to a curve, angle of intersection of two curves, what are orthogonal curves. We will see what is Rolle's theorem, algebraic interpretation of Rolle's theorem. After that, we will see Lagrange's mean value theorem, and in the last we will go with the summary of this chapter. Okay, so let's start. First is derivatives as the rate of change. dy by dx is nothing but the rate of change of y with respect to or relative to x. If a variable quantity y is some function of t, some function of time t, that is y is equal to ft, then a small change in time delta t have a corresponding change is delta y, right? A small change in delta t will have corresponding change in delta y in y. Corresponding change delta y in y, right? Thus, the average rate of change is basically delta y upon delta x. That is change in y divided by change in x, change in t. And when limit delta t tending to 0 is applied, the rate of changes becomes instantaneous, right? Because delta t is very small, tending to 0. So rate of change becomes instantaneous, and we get the rate of change with respect to time at that instant t. That is limit delta t tending to 0 del y upon del t, delta y upon delta t is equal to dy upon dx. Clear? And dy by dx is rate of change of y with respect to t. Clear? Instantaneous at some instantaneous point t, right? dy by dx is positive if y increases as t increases, right? That means if y and t both increases in same direction, then dy by dx is positive, and it is negative if y decreases as t increases, right? So if y increases and if t increases and y decreases, that means dy by dt is negative. Clear? Next thing is what is increasing and decreasing function. So let's discuss. A function f is said to be an increasing function in a to b if x1 less than x2. This implies f of x1 less than equal to f of x2. Clear? For all x1, x2 belongs to a to b. Next, a function f is said to be decreasing function in a to b if x1 less than x2. This implies f of x1 greater than equal to f of x2. Clear? For all x1, x2 belongs to a to b. So these both are conditions of increasing and decreasing function, right? Fx is known as increasing if f dash x greater than equal to 0 and decreasing if f dash x less than equal to 0. Clear? So this condition is very important. Now, if fx is known as strictly increasing, for increasing it is f dash x greater than equal to 0, and for strictly increasing, if f dash x greater than equal to 0, right? For strictly increasing, f dash x is not equal to 0, but f dash x will always be greater than 0. And similarly, for strictly decreasing, if f dash x always less than 0, right? That is f dash x cannot be equal to 0, but f dash x will always be less than 0. Then it will be a strictly decreasing function, right? Now let fx be a function that is continuous in a to b and differentiable in a to b. Then fx is an increasing function in a to b if f dash x greater than equal to 0 in a to b, right? And fx is a strictly increasing function in a to b if f dash x greater than 0 in a to b. Similarly, fx is decreasing function in a to b if f dash x less than equal to 0 in a to b, and fx is strictly decreasing function in a to b if f dash x less than 0 in a to b. Clear? So you have to keep these things in mind, right? Okay, let's move to the monotonic function. What is monotonic function? A function f is said to be a monotonic in an interval if it is either increasing or decreasing in that interval, right? So a function f is said to be monotonic in an interval if it is either increasing or decreasing in that interval. Let's see results on monotonic function. First, if fx is a strictly increasing function on an interval a to b, then f inverse exists and it is also a strictly increasing function, right? Here you have to keep in mind. Next one is if fx is a strictly increasing function on an interval a to b such that it is continuous, then f inverse is continuous on fa to fb. Clear? You have to keep these things in mind. Next one is if fx is continuous in a to b such that f double dash c greater than equal to 0 or f dash c, sorry, if fx is continuous in a to b such that f dash c greater than equal to 0 or f dash c greater than 0 for each c belongs to a to b, then fx is monotonically increasing on a to b, right? You have to remember this. Next, if fx is continuous in a to b such that f dash c less than equal to 0 or f dash c less than 0 for each c belongs to a to b, then fx is monotonically decreasing function on a to b, right? You have to keep in mind. One important thing is monotonic function have at most one root. Clear? Have at most one root. Next is tangent and normal to a curve. So let's see. If a tangent is drawn to the curve y equal to f, suppose we have a curve y equal to fx. So if a tangent is drawn to the curve y equal to fx, see this is tangent that has been drawn to this curve y equal to fx. At point x1, y1, at point some p which is x1, y1, and this tangent makes an angle psi with the positive direction of x-axis, right? So making angle psi with positive direction of x-axis. Then slope of tangent is dy by dx at x1, y1, which is equal to tan psi, right? Slope of tangent is tan psi. Clear? So this graph denotes tangent and normal, right? See, this is tangent, this is basically tangent, and this is normal, right? Normal to the curve. So the equation of tangent is at x1, y1 is y minus y1 is equal to dy by dx at x1, y1, x minus x1, right? So you have to remember this. Now length of tangent can be written as PA. Length of tangent is basically this PA. This PA is length of tangent. Clear? So PA is basically y1 cosec psi, right? Cosec psi. PA will be y1 cosec psi, right? Which will be y1 and cosec psi will be this thing, which is 1 plus dy by dx at x1, y1 root 1 plus dy by dx at x1, y1 square root upon dy by dx at x1, y1, right? This is basically cosec psi that you can calculate. Clear? Now length of subtangent. What is length of subtangent? Subtangent is basically component of the tangent along x-axis, right? So PA is the tangent, so AC will be the component of tangent, that is length of subtangent. So length of subtangent is basically y1. See, this is y1 cot psi, y1 cot psi, and cot psi is basically, see, cot psi is y1 cot psi is basically y1 upon dy by dx at x1, y1, right? Because tan psi is dy by dx at x1, y1, so cot psi is 1 by dy by dx. Clear? So length of subtangent AC is basically mod of y. Why it is mod? Because it is length, right? Length cannot be negative, right? So AC is mod of y1 upon dy by dx at x1, y1. Clear? So this is basically tangent. Now let's discuss about the normal. The normal to a curve at point P is a line perpendicular to the tangent C. This normal is basically perpendicular to the tangent, right? Perpendicular to the tangent at point P and passing through P, right? Then the slope of normal is C. Slope of tangent at x1, y1 is dy by dx at x1, y1. So slope of normal is minus 1 upon dy by dx at x1 y1, right? Because m1 m2 is equal to minus, we all know that, for two perpendicular lines. Now equation of normal can be written as y minus y1 is equal to minus of 1 by dy by dx at x1 y1 into x minus x1. Right, length of normal PB. Length of normal is basically PB. Clear? So PB can be written as C. Length of normal is y minus y1. Equation of normal is y minus y1 minus 1 upon dy by dx at x1 y1 x minus x1. Length of PB is basically y1 sec psi. PB is y1 sec psi. Clear? Which is equal to sec psi can be calculated as root over 1 plus dy by dx at x1 y1 square. So PB is basically mod of y1 root over 1 plus dy by dx at x1 y1 square. Now, since normal is PB, so subnormal will be component of normal on the line on the x-axis, right? So length of subnormal will be BC. Clear? So length of subnormal is BC is equal to y1 tan psi. Clear? So BC will be y1 tan psi. Clear? Which is equal to y1 dy by dx at x1 y1. Clear? So these things you have to remember. Clear? Next one is the angle of intersection of two curves. The angle of intersection of two curves is defined to be the angle between their tangents. Clear? Simple thing. Angle between their tangents to the curves at the point of intersection. Clear? So angle between two curves is basically nothing but the angle between the tangents at the point of intersection. Right? So the angle between tangents of two curve y is equal to, suppose we have two curve y is equal to f1x and y equal to f2x is given. So the angle between tangents of these two curves is tan phi, which is m1 minus m2 upon 1 plus m1 m2, right? So m1 m2 can be calculated as dy by dx at x1 y1 and dy by dx at dy by dx 1 at x1 y1 for curve 1 and dy by dx for curve 2 at x1 y1, right? So tan phi is basically mod of dy by dx of curve 1 at x1 y1 minus dy by dx for curve 2 at x1 y1 upon 1 plus dy by dx of curve 1 at x1 y1 into dy by dx for curve 2 at x1 y1, or this can be also represented as mod of m1 minus m2 upon 1 plus m1 m2, right? So this is the basically angle of intersection of two curves. So let's move to the orthogonal curves. What is orthogonal curves? If the angle of intersection of two curves is right angle, the two curves are said to be intersect orthogonally, and the curves are called orthogonal curves, right? So if phi is equal to pi by 2, that means m1 m2 is equal to minus 1, right? Therefore dy by dx at 1 into dy by dx at 2 is equal to minus 1, right? Note, two curves touch each other if m1 is equal to m2. Clear? Two curves touch each other if m1 is equal to m2. Clear? You have to remember this. So this is orthogonal curves. Next is Rolle's theorem. So let's discuss Rolle's theorem. Let f be a real valued function defined in a closed interval a to b such that condition 1, fx is continuous in closed interval a to b. Second condition, fx is differentiable in the open interval a to b. Next condition, fa equal to fb, then there is some point c in the open interval a to b such that f dash c is equal to 0. Clear? So this is the statements of and conditions of Rolle's theorem. Geometrically, it represents c. fa is equal to fb, right? And function fx is differentiable in open interval a to b. Clear? Here fa is equal to fb. Function is differentiable in a to b and continuous in a to b. Clear? So there must exist at least one point. There must exist at least one point where f dash c is equal to 0. Clear? Here f dash c is 0. Clear? F dash c is basically 0. Here f dash c is 0. Here f dash c is 0. Clear? So graph of a differentiable function satisfying the hypothesis, this hypothesis of Rolle's theorem. This is the graph. So there is at least one point C between A to B. You can see this, such that the tangent of the graph at point C or FC is parallel to x-axis, right? Which is horizontal tangent. Clear? So this is the basically statements and geometrical meaning of Rolle's theorem. Clear? So let's move to the algebraic interpretation of Rolle's theorem. So between any two roots of fx roots of a polynomial fx, there is always a root of its derivative fx, right? So between any two roots of a polynomial function fx, we have polynomial function fx, and between any two roots of the fx, there is always the root of its derivative fx, right? Clear? You have to keep in mind. Now let's move to the Lagrange's mean value theorem, which says let f be a real function continuous on a closed interval a to b and differentiable in the open interval a to b, then there is at least one point c in the open interval a to b such that the graph of continuous function explains the Lagrange's mean value theorem such that f dash c is equal to fb minus fa upon b minus a. You can see the graph. F dash c is equal to fb minus fa upon b minus a. Geometrically, for any chord of the curve y is equal to fx, there is a point on the graph where tangent is parallel to this chord, right? Tangent is parallel to this chord. Remarks in the particular case where fa is equal to fb, right? When fa is equal to fb, the expression fb minus fa upon b minus a becomes 0, right? Thus, when fa is equal to fb, f dash c is equal to 0 for some c in a to b, right? Thus, Rowe's theorem becomes a particular case for mean value theorem, right? Clear? Mean value theorem says that if fa is equal to mean value theorem says that if a function is continuous in a to b and differentiable in a to b, then there is at least one point in C where f dash c is equal to fb minus fa upon fb minus c. This is mean value theorem. And Rowe's theorem says that there exists at least one C such that f dash c is equal to 0. And one condition added is fb is equal to fa. So Rowe's theorem is basically a particular case of Lagrange's mean value theorem, right? So you have to keep in mind, clear? Right? Basically, Rowe's theorem gives a particular result for a particular case where fb is equal to fa. And Lagrange's mean value theorem gives the generalized case for all the cases, right? Gives f dash c for generalized cases for all the conditions of fa and fb, right? So you have to keep in mind. Next is summary of this chapter. In this chapter, we have seen derivatives as the rate of change, in which we have seen dy by dx is nothing but the rate of change of y relative to x. If a variable quantity y is some function of time t, that is y is equal to ft, then a small changes in time delta t have a corresponding change delta y in y. Thus, the average rate of change is equal to delta y upon delta t. We have seen increasing and decreasing function. After that, we have seen monotonic functions, which is a function f is said to be monotonic in an interval if it is either increasing or decreasing in that interval, right? After that, we have seen different results on monotonic functions. We have seen tangents and normal to a curve. We have seen angle of intersection between two curves, which says the angle of intersection between two curves is defined to be the angle between their tangents to the curves at their point of intersection, right? After that, we have seen orthogonal curves, which says if the angle between angle of intersection of two curves is right angle, the two curves are said to be intersect orthogonally, and the curves are said to be orthogonal curves. After that, we have seen Rowe's theorem. We have seen what is algebraic interpretation of Rowe's theorem. After that, we have seen Lagrange's mean value theorem, right? And we have also seen that Rowe's theorem is a particular case of Lagrange's mean value theorem. Clear? So in this way, we have studied the topic application of derivatives. Clear? Okay. Thank you so much.